Welcome to our September installment of the Summer 2022 webinar series sponsored by NIST. Today we have tutorial on likelihood ratios with applications in digital forensics. Your speakers today are Rachel Longjohn and Dr. Parik Smith. Rachel is a PhD student in the Department of Statistics at the University of California, Irvine, and works closely with Dr. Parik Smith, who is the Chancellor's Professor and works both in the Department of Computer Science and Department of Statistics at the University of California, Irvine. Dr. Smith is also an Associate Director and the Founding Director of the Center for Machine Learning and Intelligent Systems, Co-Director for the HPI Research Center in Machine Learning and Data Science, and an affiliate faculty member for the UCI Steckler Center for Responsible, Ethical, and Accessible Technology. Rachel, take it away.
Great. So hi, everyone. Welcome to this webinar sponsored by the Center for Statistics and Applications in Forensic Evidence, also known as CSAFE. My name is Rachel, and today we'll go through our webinar tutorial on likelihood ratios with applications in digital forensics. So kind of what we just said in our introduction, but again, my name is Rachel. I'm a PhD student at UCI in the Department of Statistics, and for CSAFE, I work in digital evidence specifically.
And I'm Parik Smith, and I'll speak for the first few minutes and then hand back to Rachel. Next slide, please, Rachel. So this is a high-level picture of digital forensics. On the left, we see devices, cloud accounts, and so forth, associated with crimes, with suspects, and much of digital forensics in the past, and much of it currently is concerned with how do we extract such data reliably from the devices, for example, from user activity logs. Next slide, Rachel. And we're interested in the right-hand side of this picture. As the data is extracted, images, text, events, geolocation, how can we analyze this data? In particular, what we'll be talking about today is how can we do quantitative statistical inference in the form of likelihood ratios to answer questions of interest. Next slide. The type of data that, as many of you will be familiar with, is often event type data where there's an ID, maybe the account name. The data is often categorized into which app was opened or which file was opened or which URL was browsed. There's typically a timestamp for the event. There may be geolocation data, and there may often be metadata such as user-generated text. So this provides very rich data source, which is good, but it also makes it complex to analyze. Next slide. I'm going to give you an example of what some of this data looks like. This is a complicated picture, so let me explain what we're looking at here. This is URL requests, web requests from a browser on a desktop for a particular user. And the x-axis is time. Particular events, particular requests for web pages. And so as each single vertical line, it corresponds to one day. The y-axis goes from midnight at the bottom to midnight again at the top. And you can see a pattern in this. Each day, there's very little activity, some activity at nighttime until about 8 in the morning, going up the y-axis. And then you see bursts of activity during the day and then tapering off in the evening. You also see some interesting gaps in the data where the user was not using the desktop, particularly to the right. There's a big gap of over a week. Next slide, please. Now, what we've overlaid here is laptop data owned by the same individual. Those are the red dots. So the blue is the desktop, the red is the laptop. And these are also web browser requests. And we can see visually a pattern here that the red dots are consistent with the blue in the sense that they generally don't overlap and they tend to happen either before or after or during gaps in the blue data. So we see, for example, that that gap on the right is now filled in with laptop data. So perhaps the individual was traveling and brought the laptop with them. And also at the very top, we see more laptop activity in the evening, so a little bit in the morning before the desktop gets used. So if we wanted to answer the question, was this data generated by a single individual or by two different individuals? Our pattern recognition would tend to suggest visually that there's a lot of evidence that it's a single individual. It's consistent with a single individual. So visually, this is what this looks like. The question we're interested in is how can we quantify this? Can we look at this in a more quantitative fashion and come up, for example, with likelihood ratios? Next slide, please. So in our group in the past, we have looked at geolocation data, and this is increasingly common type of data in digital forensics. So let's say we have geolocation data associated with a crime, data set A, and data set B, geolocation data from an individual suspect's device. How likely is it that the suspect generated both sets of data? This is a common question. We've done some work on this. I put some references at the bottom, but if you focus on the picture in the middle, again, visually, we can see on the left, it's more consistent with a single individual. The geolocations are the same for the green and the yellow dots. On the right, it's less consistent with a single individual, suggesting perhaps two different individuals, green and yellow. Next slide, please. Another area where these types of techniques this type of data comes up is forensic text analysis. I've referenced a recent paper here on this topic, where now the question is, you have two documents or two sets of text messages, and you're interested, were these generated by a single individual or not? And the paper I've referenced proposes a likelihood ratio framework. So we're not the only group looking at this. There's other work emerging on using likelihood ratio ideas that have been used in other forensic areas and applying them to digital evidence. So with these slides as an introductory motivation, I'm now going to hand back to Rachel, who's going to tell you in more detail how we build likelihood ratios for these types of problems. So Rachel, back to you.
Thank you, Pork. I'll be speaking for the remainder of the webinar. So following this general introduction, we'll have three remaining parts to the webinar. So the first part will be an introduction to likelihood ratios. And as suggested by the title of the webinar, we'll be going through this tutorial style. So we'll build this up from basic concepts in probability and walk through very simple toy examples to introduce the concepts. The second part is, once we have built the foundation for the concept of likelihood ratios, we'll talk about how we can actually calculate it. And for this webinar, we'll go through specifically Bayesian computation methods, but we'll briefly discuss some other strategies as well. And then for the remaining part, we'll talk about our recent work in applying the methods that we would have built up in the first two parts of the webinar to digital forensics data specifically. We'll talk about some experiments that we've conducted with email, mobile app usage, and geolocation data. We'll show the results from these experiments, and then we'll conclude with a discussion of these results and potential future directions for this line of research. So to start out with the first part of the tutorial section, we'll go with a very classic statistical example of tossing a coin. And this example will ground the concepts that I'll introduce for the first two parts of the webinar. So in this example, suppose that we have this two-sided coin, coin A, and we're allowed to flip this coin some number of times and document the results. So let's say that the two sides of the coin are heads and tails. So we can flip this coin a number of times, and we'll call that number of times that we flip it N1. And by document the results, we will count the number of times that the coin lands on heads. And so that's what the results will look like here. Now, suppose also that we have the results of flipping another coin N2 times, but we don't know which coin was used to generate these results, where the results are still in the form of number of heads. And this has been outlined in a dotted line to indicate that we don't know which coin has generated these results. So using these two pieces of data, we'd like to ask the question, were the N2 flips generated by coin A? And this is the question we'll work to address through the first two parts of the webinar. And so for this example, we'll make some simplifying assumptions to make things a bit easier on ourselves. The first is that the conditions under which we flip all of the coins will be the same. And so, things like wind resistance and stuff like that doesn't come into play here. And also suppose that for this population of coins, how often they land on a certain side is unique. So in the universe, there's only one true fair coin that lands on heads 50% of the time. And so to start with our framework, let's have a proposition. The proposition here is that coin A was the coin that generated these unknown source flips. And in forensics, this kind of proposition is often called the same source proposition. And we'll denote it by HS here, where S stands for same source, and H is used for the word hypothesis, which is sometimes used interchangeably with proposition. On the other hand, we could also have some different source propositions, and there's a couple ways that we can lay these out. So here's some examples. The first is we could say that instead of coin A generating these flips, it was coin B that generated these flips. So we have a specific alternative source. We could also say instead of it being coin A, it was either coin B or coin C that generated these flips. Or we can leave this alternative population broad to be any other coin in the universe, just not coin A generated these N2 flips. And so it's important to note that both the same source proposition and any of these different source propositions that we've used as examples here cannot both have happened. They cannot both be true. And another thing to note is that sometimes when people are laying out these propositions, they'll use the terms HP and HD, where P is used to stand for prosecution and D is used to stand for defense. Okay, so returning to our same source proposition, note that this is actually a same specific source proposition. So we're saying that coin A generated these N2 flips. Another way we might do this is to have a same common source proposition, where instead we can just say the same coin was used to generate both sets of flips, but we don't care which coin it was. So it could be coin A generated both of these flips, or coin B generated both of the flips, or any other coin in the universe, just that it was the same coin that generated both sets. So in this case, our different source proposition would just be that the same coin did not generate both flips. So as an example, it could be that coin A generated those flips, which we know, and coin B generated the unknown flips, or any other example where the coins are different. But we'll stick for this webinar to the same specific source proposition. And we will also hone in on this last different source proposition where we say that coin A did not generate the N2 flips. So what do we have as the evidence in this case? First we have our known source data. We have the number of times after flipping coin A that it landed on heads, and we'll call that number of heads X1. We also have the set of unknown source data, which is the number of times that the unknown coin landed on heads. We'll call that X2. So when we take both of these pieces together, this comprises the evidence, which we'll sometimes use E to denote. And so specifically in our case, E is X1 and X2, but more generally, the evidence consisting of known source data and unknown source data is a common form of comprising the evidence in forensics. And so to get to the likelihood ratio, we're going to build up the odds form of Bayes' theorem. So you've probably heard of Bayes' theorem in your intro to probability class. So first, we're going to lay out the concept of odds. So the odds in favor of the same source proposition relative to the different source proposition is the ratio of these two probabilities. So the probability that the same source proposition is true divided by the probability that the different source proposition is true. And so this might look a little bit confusing, but you've probably heard the term odds before. So for example, think about a sporting event where you hear something like the odds are 3-2 in favor of team S. All this means is that the probability that team S wins divided by the probability that team S does not win is equal to 3/2 or 1.5. So a similar concept will apply when we talk about the odds of these source propositions. So in forensics, the particular set of odds is called the prior odds. And why is that? That's because information found in the evidence has not yet been incorporated into these probabilities. And so this is prior to incorporating that information. After we incorporate that information, the odds that we get will be called the posterior odds. So post incorporating the evidence information. And those are going to look like this. So all this means is that we are accounting for the fact that we've observed this particular evidence E. And so that's what this notation is here. We're conditioning on observing that evidence. And so in words, what the posterior odds are, the odds in favor of the same source proposition relative to the different source proposition, given that this evidence E was observed. And so if you were to Google Bayes' theorem or from your intro to probability class, or you clicked on the Wikipedia link, this is the version of Bayes' theorem that you'd see. So we're going to use this to get to the odds form of Bayes' theorem. Specifically, remember back to the posterior odds, we had the ratio of those two probabilities where now we're accounting for the evidence. So this is just the term that was on the top. It's the probability of the same source proposition, conditioning on the fact that we've observed this particular evidence. And all we're doing is taking this theorem and plugging in the terms that we care about, the same source proposition and the evidence. And now we're going to do the exact same thing for the denominator. So this is the same term, it's just now we have HD instead of having HS in here. So now we have the two pieces of the posterior odds. And so we're going to keep these in mind and we're going to stack them on top of each other to get the posterior odds. So we'll put the blue pieces on the top and the red pieces on the bottom. And notice that we have two matching terms here. We have the probability of the evidence. And so these things can cancel out. So we're left with just this term here. And there's some things that we should recognize from just a few minutes ago. We can see inside this equation the prior odds. And so we'll separate this out to make it more clear. And so now this is the odds form of Bayes' theorem. And there should be three pieces, two of which we should recognize already. First, we have the prior odds here on the right. We have the posterior odds here on the left. And then there's this mystical term in the middle that we haven't talked about yet. And this is the star of the show. This is the likelihood ratio. So from this equation, we can see that we can multiply the prior odds and the likelihood ratio to arrive at the posterior odds. And in words, sometimes you'll see this description saying that the likelihood ratio measures the relative probability of observing the evidence under the same source proposition and the different source proposition. What does this actually mean, though? So this is that same formula for the likelihood ratio, now just pulled out to be on its own. And in our particular example, remember that the evidence is x1, the number of heads from coin A, and x2, the number of heads from the unknown source coin. So we have our same source proposition that coin A also generated the N2 flips, and the different source proposition that coin A did not. If we were to get, through some process that we don't know about yet, a likelihood ratio value of 10, what does that mean? That means that observing these particular sets of coin flips is 10 times more likely if coin A generated the N2 flips than if coin A did not. On the other hand, say we got a likelihood ratio of 0.25 or 1/4, then observing these particular coin flip results is 4 times more likely if coin A did not generate those flips than if coin A did. And so we can think about this more generally. What if we just get a likelihood ratio that's greater than 1? That means that if we look at this term at the top term is larger than the bottom term, so we get a likelihood ratio greater than 1. And this means that in a more generic sense, observing these results is more probable if coin A generated the flips than if coin A did not. And on the other hand, if we get a likelihood ratio less than 1, then this term on the top is less than the term on the bottom. And this means that observing these flips is more probable if coin A did not generate the flips than if coin A did. And then there's one case that I ignored on the last slide, which is what if the likelihood ratio equals 1? And that just means that observing these results is equally probable if coin A did or did not generate those flips. So getting a likelihood ratio greater than 1, more probable, what does that actually mean for our source propositions? So in general, this would support the same source proposition, whereas getting a likelihood ratio less than 1 supports the different source proposition. And the equal to 1 case doesn't really help us distinguish between the two. So this is a table reproduced from Dr. Colin Aiken's textbook that shows that even getting the same likelihood ratio value can have a different effect in the context of different values for the prior odds. So let's say that before incorporating evidence information, the prior odds that we had regarding our source propositions was 1/10,000. Getting a likelihood ratio of 1,000, and remember we multiply these two things together, would give us a set of posterior odds of 1/10. But going all the way to the last row of the table, if we had prior odds of 100, then getting a likelihood ratio value of 1,000 would lead us to posterior odds of 100,000, so strongly in favor of the same source proposition after incorporating the evidence information. So the takeaway from this table is that even getting the same value of the likelihood ratio can have a different effect on how we evaluate the evidence in the context of different values for the prior odds. So in this toy example so far, we've been focusing on the case where the evidence is in the form of these counts from coin flips. And this doesn't come from nowhere. Count data has been used elsewhere in forensics. So here are a few examples. Counts of illicit versus illicit drugs and samples for chemical analysis. This was studied in this 2009 paper. There's also counts of question documents coming from particular printers. And this was studied in this 2011 paper. And also for the purposes of author attribution, we could count function words in suspected criminal messages. And this has been very recently studied in this paper from earlier this year. And I'll also make a note here on this slide that there's this technique that's called score-based likelihood ratios. And this is a likelihood ratio that's based on a similarity score between the two pieces of the evidence. And we're not going to talk about this today, but it's worth pointing this out as an alternative. So I'm getting to the end of section 1 of the webinar. So I'll just recap everything that we've talked so far about in this intro. So in our toy example, we have the data, which has these two pieces. It has the known source data and the unknown source data. We also have our forensic question, were these N2 coin flips generated by coin A? And we have our source propositions, the same source proposition and the different source proposition. And we have this concept of the likelihood ratio. So what we'd like to do next is actually find a way to get our value of the likelihood ratio in this example. So that will lead us to section 2, which is calculating the likelihood ratio. So how do we actually do this? Here's the formula that we want to get, and we're going to break this process down into 3 steps. The first step will be we're going to specify models for the 2 probabilities under each of the source propositions. So specifically, these are the 2 probabilities that are in the likelihood ratio right up here. The second step will be we'll decide how to handle the underlying parameters in the models that we specified in the previous step. And we'll talk about 3 scenarios or strategies for doing this. The first will be, what if we're in this magical case where we know the parameters? What is the effect on the likelihood ratio? And then what if we do frequentist or Bayesian strategies? So we'll go through each of those. And then step 3 will be, we'll derive the likelihood ratio under whatever decisions we've made from the previous 2 steps. So let's start with step 1. So this first step is specifying models for the 2 probabilities under each of the source propositions. So let's do this for the same source proposition first. So this is assuming that coin A generated the flips from the unknown source coin. To make things easier for ourselves, we'll assume that each coin flip is independent. The result of one flip does not affect the result of another flip. And we'll also say that the probability that coin A lands on heads is some number between 0 and 1, and we're going to call that number theta 1. And so this is the binomial likelihood. This is for the situation that we've laid out in these first 2 bullet points. So we have N1 flips. We can see that in the likelihood here. We get X1 heads, and then we have the probability of landing on heads raised to the number of heads, and then the opposite for landing on tails. And we have the exact same thing for the other set of flips. So this is just the exact same likelihood that we have above. And notice that because we're saying that the same source proposition is true, that these X2 heads were generated also by the same probability from coin A, theta 1. And again, these are just simple binomial likelihoods. So using this model, remember that in this slide here, I'm showing 2 separate equations, but in the likelihood ratio, we have the probability of both X1 and X2. So how are we going to handle that? We're going to split up this joint probability, the probability for both pieces, into 2 through our conditional independence assumption. And then we'll just plug in those 2 pieces. So we're just going to multiply those 2 pieces together. And that's going to be the value to remember going forward. So now what about under the different source proposition? So again, we'll assume that the coin flips are independent. And this time we'll still assume that the probability that coin A lands on heads is theta 1. But this time the probability that the unknown source coin lands on heads, we're going to call that theta 2, where theta 2 is also some number between 0 and 1, but it's not equal to theta 1. So we have the same binomial likelihood for the coin A flips. But this time we have a very similar looking binomial likelihood, except for the key change is that now we have theta 2 in here instead of theta 1. And so the difference here is that theta 1 does not equal theta 2. And so next we'll move on to step 2, now that we've specified our model for those 2 probabilities. So we need to decide how we're going to handle theta 1 and theta 2. So let's assume in the totally unrealistic situation where we know what theta 1 and theta 2 are, this implicitly affects our underlying source propositions because we know these quantities. So what we're saying is that if we know theta 1, that not only do coin A generate these flips, but we know that the probability of coin A landing on heads is this theta 1. And if we know theta 2, then that means under the different source proposition, we know that some coin with the probability of landing on heads theta 2 is the one that generated the unknown source flips. And remember that these probabilities of landing on heads are unique from our simplifying assumptions. So that means that we know it was some coin, specifically we can call it coin B, that landed on heads. So now that we know theta 1 and theta 2, let's go into step 3, which is deriving the likelihood ratio. So again, here's the formula for the likelihood ratio. You'll see this many times. And using the conditional independence assumption that I mentioned before, we can split up these two probabilities. And all we're doing is plugging in the binomial likelihoods from the previous 2 slides. So this is just the product of the 2 binomial likelihoods on the top and the product of the 2 binomial likelihoods on the bottom. And we can see there's a lot of repeats in the terms here, so a lot of this cancels out. And so what we're left with is this term that has in it theta 1 and theta 2, x2 and n2. And so the important things to notice here are that only the unknown source flips matter in this calculation. We don't have anything to do with the n1 flips in here. And that's because knowing theta 1, we have all of the information that we need from point A. We don't need to see its reference data. So basically with this formula, we're just asking ourselves, does theta 1 or theta 2 explain the unknown source flips better? So what if we're not in that magical universe where we know the parameters and we're in something more realistic? So we'll revisit step 2 in this case. We'll say that theta 1 and theta 2 are unknown. And now we'll go back to the source propositions that were our goal to begin with. We have the same source proposition, coin A generated the flips, and the different source proposition that coin A did not. The strategy here will be to replace these parameters with a point estimate, which is in the frequentist style. And so while this sounds good in theory, what we're going to be doing is fitting the model and evaluating the likelihood ratio using the same data. And this is always going to favor the 2-parameter model. So let's think about this in a little more detail. Under the same source model, we need to estimate only theta 1 because this is the parameter that is underlying both sets of coin flips. So to do that, let's just take the relative frequency of heads across both sets. So we'll just count up how many times we got heads and how divided by the total number of flips. And we'll do that across both sets of coin flips. And that'll give us our estimate for theta 1 under the same source proposition. We can do a very similar thing for the different source model, except for now we have to get 2 estimates. And so we'll use the relative frequencies from coin A to estimate theta 1 and the relative frequencies from coin B to estimate theta 2. And for those that are familiar, these are the maximum likelihood estimates. And so what we could do in this case is, and also note that the 2-parameter model will always fit better in this case for the likelihood ratio. And so how could we handle this? What we could do is we could split up our data. We could use some of the data to estimate the model parameters and then use the rest to evaluate the likelihood ratio. We could also turn to a background or a reference database that we use to estimate the models and then evaluate the likelihood ratio using our evidence. But both of these approaches require having more data than we have or using less data to evaluate the likelihood ratio. So keeping that in mind, we'll move to a Bayesian strategy for handling step 2. So again, theta 1 and theta 2 are unknown. But our strategy now is going to be to put a prior distribution on them. So specifically, we'll put a beta distribution on the 2 parameters. And keep in mind that the beta distribution has these 2 parameters that we need to specify. We'll call them alpha and beta. And for those that are more familiar with Bayesian concepts, this is the conjugate prior for the binomial likelihood. We could specify different distributions for theta 1 and theta 2, but for simplicity here, we'll have them both come from the same beta distribution. So the beta distribution has these 2 parameters that kind of govern what it looks like. And so we could set both of these parameters equal to 1. And in this case, we just get the uniform distribution. So any value for the thetas that are between 0 and 1 are all equally likely. So we just see this flat line here across all values. We could also increase these terms, and that's going to make certain areas along the 0 to 1 x-axis more likely. So in this case, we've given alpha a value of 5 and beta a value of 2, and we can see that we get a right skewed distribution. So we favor larger values of theta, so values closer to 1. And we could also get a left skewed distribution or even something that's still centered but has a higher peak than this flat line here. So this gives us the chance to incorporate information that we might know ahead of time about these underlying probabilities. And we have the flexibility to capture a lot of different levels of uncertainty in these parameters here. And I will point out, though it's not important to remember the exact formula, that this is the PDF for a beta distribution. And inside it has this beta function that takes as input the two parameters that we'll specify. And the formula for this function isn't too important, but we just have to remember that it's something that's easy to compute. So all we need to do is give in basically any programming language a value for alpha and beta, and we'll get out a value for the beta function. So let's talk about step 3 under this strategy. So again, here's the formula for the likelihood ratio. Let's just start by looking at the numerator with these specifications. So here's the numerator. What we're going to do is we are going to now condition on a value for theta1 and multiply it by our prior distribution for theta1. And what this is doing is averaging across the possible values of the parameters. So we're saying now we want to incorporate all possible values for theta1. So from those prior distribution pictures I showed, and we want to weight this by how probable those values of theta1 are. So that's all this notation is saying. We have this integral sign. We're just averaging across all of these possible values, and we're taking a smarter average by incorporating the information from our prior distribution. And so again, because of the conditional independence assumption, we can split up this first probability into the two separate probabilities. And the prior distribution doesn't depend on the source proposition, so we can get rid of this extra conditioning statement that's here in the last probability. And we can do something very similar for the denominator with, in general, the same 3 steps. And we get very similar looking integrals, except for now there are 2 integrals, one for each of the 2 parameters that we need to average over. And so each of these 3 integrals look very similar. So let's just take a look at one and see what we can do about it. So this is the integral of the number of heads for coin A under the different source proposition, and we are averaging over possible values of theta1. So if we plug in things that we've already seen, we plug in the binomial likelihood and we plug in the beta prior, we have this ugly looking integral that has a lot of terms in it. And we can go through step by step how we can actually manipulate this integral to get to something nicer. But we won't go through each line of this. I'll just say after some algebra and integration tricks, we end up with this formula. And though this still doesn't look super friendly to the eye, this is actually much easier to work with than this integral on the top line. And so we have everything in here, something that we know. We know n1, we know x1. And remember, we have these beta functions that are easy to calculate with these known inputs. So this is the integral that we had in the formula that we got on the previous slide. And we can do very similar things for those other 2 integrals that we had. So if we were to go through that same process, we would get this formula, which is the same thing that we have above. It's just now we have x2 and theta2 instead of x1 and theta1. And this is the formula for the one on the numerator, where now we can see we have both sets of flips kind of smushed together. So all we have to do is plug these into the formula for the likelihood ratio. So when we do that, here's the formula again. And we get this messy looking expression where we have all 3 things kind of pushed together. So what's nice about this, though, is that there's a lot of terms that are on both the top and the bottom. So again, we're going to get a lot of things that cancel out here. We're going to get all of these combination terms cancel out entirely. And then 2 of these beta functions are going to cancel out as well. So all we're left with is this ratio that has 2 beta functions on the top and 2 beta functions on the bottom. And again, what's important to note here is that we only need to input the data from our evidence and then whatever we specify as the prior parameters. And understanding exactly what this formula is doing isn't too important for this webinar. We just need to know that it's something that we can compute easily with these 2 things. So let's go through some examples of if we were to actually do this procedure in our coin toss example. So let's say that we specify a uniform prior distribution for our two theta values. So just that flat line, all values are equally likely, and we don't have a preference for any particular window. What would happen if we got out of 5 flips for coin A, 2 heads, and the exact same thing from the unknown source coin? If we were to plug into this formula, we would just get a likelihood ratio value of 1.56. So notice that we have identical patterns of heads here. And so the likelihood ratio is greater than 1, indicating more support that these were generated by the same source. So that makes sense since we have these identical patterns. On the other hand, if we had different patterns, out of 5 flips, we got 3 heads for coin A and 1 head for coin B. We get a likelihood ratio of 0.78. So this is less than 1, indicating more support for the different source proposition. What if we had a lot more data? We were able to flip these coins a lot more times. So let's say we got 10 heads for both coin A and for coin the mysterious coin. In this case, we get a likelihood ratio value of 9.43. So this is now greater than 1, again, indicating support for the same source hypothesis. And then what if out of the 100 flips, we got different patterns? We had 10 heads still for coin A, but now 30 heads for the unknown source coin. In this case, we'd get a likelihood ratio value of 0.013. So again, less than 1. So as I've pointed out, similar patterns, likelihood ratio values greater than 1. But with different patterns, we get likelihood ratio values less than 1. And another interesting thing to note from this example is when we have less data, so the top 2 examples here, we had only 5 flips, so we had little data. We get values that are closer to 1, so closer to the neutral value. But when we have more data, we can make slightly more extreme statements. We can get values further away from 1 for the likelihood ratio. So this indicates that our formula for the Bayesian likelihood ratio kind of behaves as we would expect a likelihood ratio to. So we're now approaching the end of the second section here about calculating likelihood ratios. So I'll just go through what we've talked about in this section. We have a binomial model for the results of the coin flips under each of the source propositions. We discussed 3 different strategies for handling the model parameters. What if we had a set of known parameters, and this is not realistic and also implicitly affects our goal source propositions? And what if we use a frequentist strategy for estimating these parameters, and we said that this favors the different source model, the 2 parameter model. And so we need more data for estimation, or we need to somehow do a separate data splitting technique. Or we can do a Bayesian strategy for estimating these parameters, but this requires that we specify some prior distributions. So we have to specify those alpha and beta terms. And so we'll stick with the Bayesian method of estimating these as we go into the last section of the webinar, which is going to be our applications to digital forensics. So this is some of our recent work. So going back to the very beginning of the webinar with the examples of data that Pork was talking about, we're going to focus on user-generated event data. And so generally speaking, this event data will have, so each kind of row in this data set will have 3 major components. We'll have the ID that identifies the user, the device, or the account. We'll have some event that we're interested in. And these are user-generated actions on the device. For example, interacting with a certain app or sending emails, things like that, and the time at which these events occurred. And I did want to note that for the applications to digital forensics section, if people are interested in more details, there are some conference presentations that we've given on this that are available on the CSAFE website. Should be under my name and digital evidence, if anyone's interested in looking at those after the webinar. So looking at these 3 pieces, we have a set of events of interest, and tying this back into the coin example that we've been looking at this entire time. In that example, the set of events that we were looking at had 2 events of interest. It was either heads or tails for the coin. Now we're saying that we have many possible events that could happen, and so way more than 2. And specifically, we'll say that the number of events possible is capital K. So again, this could be things like interacting with apps or sending an email. And we also have this ID that ties particular groups of events together. So what does the evidence look like in this case? It's going to look very familiar to the toy example that we talked about, where we have a set of N1 events that were generated by a known person of interest that we'll call person A. And again, these are all of that similar format ID event timestamp. And we also have a set of N2 events that were linked to a crime that were generated by an unknown person. So we'll do a very similar procedure as we did with the coin example. We'll count the occurrence of the number of events, except for now we're counting across all K events that are of interest. So let's just say that we have 5 events that we care about. We might get something like this, where we count the number of times each of the 5 events occurred in the known source events generated by person A on their device, and the number of times that each of these 5 events occurred in the set of unknown source event counts. So some scenarios where we might want to do something like this could be the stolen device scenario. So this would be, we have the time when a device was linked to some criminal activity, and going back in the past, there's also a time when the person of interest and suspect claims that the device was stolen or otherwise lost or just not in their ownership at the time. And so they weren't the one using it in the time leading up to the criminal activity. So what we could do is we could look at the pattern of event counts from this time when this person of interest was using the device and compare that to the event counts in this time period of contested ownership, so unknown source data. Another case might be that it's suspected that a person of interest carries 2 devices on their person, so a primary and a secondary device. And in this case, we'd also want to compare the event counts. We might look at things like geolocation data, so if this person was visiting the same locations. So what are the source propositions now in this application? We have the same source proposition, which is still looks very similar to the coin example, that person A generated the set of unknown events. So they're responsible for both of these counts. We also have the different source proposition. So this posits that person A did not generate the set of unknown source events generated by somebody else. So we have these event counts from a known source over time, and we have event counts from an unknown source over time, and we have the same source in the different source propositions. So what we would expect is that if the same source generate both of these event counts, we might see similar event count distributions. On the other hand, if these sets of events were generated by different sources, we might see different event count distributions. So something like the bottom line here. So what we're going to do is show very similarly to before how we can calculate the likelihood ratio using the Bayesian strategy. And we're going to use the same 3 steps that we did in the previous section. So the first step is, again, specify the models for the 2 probabilities under each of those source propositions. So in this case, we still have x1 and x2, but now these are event counts across many different events. And we're going to say that these follow a multinomial distribution. And notice that we're in the same source proposition case. And so we have the same theta1 appearing in both of these lines here. And just note that this is a very straightforward extension of that binomial distribution that we talked a lot about earlier. It's just now we call it a multinomial, and it expands to more than 2 event categories. And we have something very similar under the different source proposition, where we have these 2 multinomial likelihoods, except for now, notice that we have different parameters. We have theta1 for the known source events, and we have theta2 for the unknown source events. So this is very similar to the coin example, where we have these 2 different probabilities governing these counts. So again, for step 2, we're going to take a Bayesian approach. We're going to put a prior distribution on theta1 and theta2. And this distribution has the name Dirichlet, and it has prior parameters alpha. And this is bold to indicate that the alpha is a vector that has k parameters in it. And again, this is just a simple extension of that beta distribution that we saw earlier, where instead of just having the 2 event categories and the 2 prior parameters, we can now expand this to the many event case. And step 3, we can derive the likelihood ratio using the decisions that we've made in step 1 and 2. So it's going to be a very similar process to what we already saw in the previous section. And we get a very similar looking formula. We get this ratio of beta functions, where again, the inputs are the prior parameters and the 2 pieces of the evidence. And so just note that this beta function is, again, just as the other two steps, a straightforward extension from the beta function that we already saw earlier in the 2 event case. So this is something that's easily computable, just given the inputs. And so we did some experiments with real world data sets, and we did this across 3 different data sets, email, geolocation, and mobile app usage data. And to set up the experiments across each of these 3 data sets, we, in general, split the data set, the time over which it was collected, into 2 halves. And we treat the first half of the data as coming from people that we know. So these are going to be the known source event counts. And we treat the second half of the data as coming from unknown IDs. Obviously, in reality, because we have access to the full data set, we know which ID generated these events. And we're going to plug in the event counts for particular values of the prior parameters and evaluate the likelihood ratio on all of the same source pairs and a random sample of different source pairs. So a same source pair means that we take the data from an ID from the first half, look at their event counts, and compare it to the same ID's second half of the data's event counts. A different source pair just means that for one ID, we pick a different ID and evaluate the likelihood ratio comparing those 2. So a little more detail on the 3 data sets that we used. The email data set comes from the Stanford Network Analysis Project. This was almost 300K emails sent over a roughly 2-month period. And each row in the data set has this format of sender ID, recipient ID, and timestamp. And these come from 655 users, and each event is someone sending an email. So the way that we specified the event categories of interest are we looked at a pool of possible recipients. So this was almost 1,000 possible recipients, and each category of event is sending an email to a particular recipient. We also looked at a geolocation data set. This was collected using publicly available geolocated tweet information. And we specifically looked at Orange County in California over a 7-month period. And each row in the data set for this case looks like this row pictured here, which has the user ID, the time at which the tweet was sent, and the latitude and longitude information. This has data from a little over 2,000 users. And the way that we identified event categories here is we divided up Orange County into census block groups. So an event type is sending out a tweet from a particular census block group. And this is what the census block groups look like in Orange County. There are obviously there's many different ways that you could divide up the area in Orange County, but we chose census block groups since they're nicely defined and provide a nice moderate resolution for looking at this area. And this gives us 1,400 possible event categories. The third and last data set that we looked at is mobile app usage data. So this is data coming from Android phones, almost 2 million records collected over a 9-month period. Each of these records is of the form user ID, and then we have these 2 pieces in the middle, the name of the app and the event type, and the time at which this happened. And so possible event types include opening and interacting with the different apps. And so we consider each of these separate event types. So for example, opening Facebook and then interacting with Facebook would be 2 different events. And this resulted in 159 event types. And the reason that this is an odd number is that there's not a possible interaction event for some of the apps. And so here are the results from evaluating the likelihood ratios on all 3 of these data sets using the same source and different source pairs. So again, we have the email, geolocation, and app data set. And the first metric that we looked at here is the true positive rate using 1 as a threshold. So we want this to be high, close to 100. We can see that we got good results on the email data set and moderately good results for the other 2 data sets. We also looked at false positive rate using 1 as a threshold. We want this to be low. And again, we got moderately low false positive rates and the lowest on the geolocation data. And we also looked at the AUC. This is area under the ROC curve metric, and we want this to be high, so close to 100%. And we can see that we got pretty favorable results across all 3 data sets, doing the worst on the mobile app usage data. We also dug into a little more detail in these results, and these are some illustrative examples of places where this likelihood ratio got it wrong. So the first, we can look at a picture here of an example, false negative. This is from the Twitter data, and these blocks are like the census block groups. And so in this case, the known source data, so again, person A, visited these two census block groups in the first half of their data. And then this is also this is an example of a positive case. They visited entirely different census block groups in the second half of their data. So looking only at their geolocation information, they did not go to similar places in their two sets of counts. And our value for the likelihood ratio suggests that these were generated by different people. And this is pretty understandable, since looking only at this data, there's no reason to think that they are generated by the same individual. On the other hand, this is an example of a false positive. So these are actually different source information, but the likelihood ratio is greater than 1. And what happened here is this person A, kind of moderately visited several different locations, but the unknown source person had very heavy visits that overlapped with one of these moderate locations. So they had a lot of data. So the likelihood ratio is a little bit sensitive to this particular case. So let's discuss a little bit of the method and these results. In addition to the experimental evaluations on real data sets, we've also done some work on theoretically analyzing this formula, and having a formula that's easy to compute makes this much more straightforward than in other methods. So specifically, we had that formula with those multivariate beta functions that had a lot of input pieces. And what we were able to do is, using the formula for those beta functions, rewrite the formula in a way that's more interpretable. And this has actually led to some useful insights in studying this. So in limiting behavior, when we go to extreme cases, we can study the behavior of the likelihood ratio under these certain conditions. And in particular, one area that this helps is deciding how to set the prior distributions. So in those examples, we just used a uniform prior distribution where we didn't have a preference for particular events. So what we could do is, actually, if we have some prior information, we could incorporate that into the prior distribution. So we could incorporate things such as how common events are into the calculation of the likelihood ratio. And just having some kind of prior that is not uniform, that doesn't favor all combinations as equally likely, we'll call that an informative prior. This can sometimes be a controversial term, but here we're just using it to mean not a uniform prior. And what we can do is, incorporating this information about the commonality of events, we can make observing shared common events less impactful on the likelihood ratio. So for example, in the geolocation case, a lot of people might go to the census block group where Disneyland is. And so seeing two people go to Disneyland might be less impactful than seeing two people go to some census block group that rarely gets any visits. So using this information in the prior, we can make seeing shared events that are more rare more impactful in the calculation. Another thing is we want to look at the calibration performance of these likelihood ratios. So this is asking the question, are we systematically understating or overstating the value of the evidence? And from our experiments, we found that the likelihood ratios generated through this formula are generally on the right side of the threshold, but can sometimes be too extreme. And so this is something that we will be looking at as future directions. So I'll summarize the applications that we've talked about in this section of the webinar. We extended that simple coin example, the 2-event case, to the many event case. We demonstrated using the Bayesian strategy to calculate the likelihood ratios in this many event case. We showed how this might be applied to user-generated event data in digital forensics. We showed the results of experiments using real-world data sets. Talked very briefly about some theoretical analyses that we can do with this formula because it's easy to compute given these inputs. And the takeaway from this so far is that this kind of technique shows promise, but is not yet ready to be at the stage where it's used in court, particularly in reference to the calibration issue. But it could be useful in other stages of the case, such as the investigative or discovery part. And so there's also some limitations to this method, and these are leading to current directions that we're thinking about extending this research to, and things that we'll continue working on into the future. So one example is incorporating the order that the events occurred. So instead of just counting, we can say we know that this event came before this one, came before this one, and incorporate that information into the calculation. And even more generally, we can incorporate that timestamp variable a little more carefully. So we can also think about the time between events as well. Another thing is that we could, instead of incorporating a single time of change, a possible window of change points. So what this looks like is I showed this timeline earlier where we had event counts when the source was known, and we had this nice dividing line, and then event counts when the source was unknown. So what if instead we have the more realistic situation where there's a window of possible change in ownership? And how can we incorporate this into the likelihood ratio calculation? So we have some preliminary ideas for this. We can include this in our Bayesian strategy as another variable, the time that the device changed ownership. And we can also do a smart averaging over this and get a formula for the likelihood ratio. So this is something that we're starting to explore right now. Here are some great references that I've used throughout this webinar and suggest to anyone that's looking for more information. This top section is on likelihood ratios kind of in general, used in the first two parts of the webinar. We also have some specific digital forensics references that we used earlier in the talk. And then those examples I mentioned of count data also being used in other areas in forensics. And here's my contact information if anyone has more questions. We also have a project website available here, and you can scan this code to get to the website. We also have a manuscript that is currently being reviewed on this work. So if you can reach out to me, and after that gets published, I could send a preprint along if anyone wants more information or more details. So thank you.
Thanks, Rachel. I guess it's time for questions, if there are questions.
Karen,
I see.
first of all, says, very nice talk, thank you. And then says, how do frequentist methods for testing equality of thetas work?
Oh yeah, okay, great question. I took out some of the details on the slide here, but basically I showed those relative frequency estimates, and the way that we derived it is you would plug that into the formula for the likelihood ratio that we had. And so now you would get a formula that's in that's a function of those estimates. So it has the same data using for the estimates and then we'll evaluate that. So it's just a function of the data. A good reference for that is the DeWeed paper that I put in the suggested reading, where they talk about this procedure and how it works. So that's kind of the template that we used there. And again, as we mentioned, when we do that, we use the same data to estimate and to evaluate. We run into the problem where it always favors the two parameter model, since that's the data that we use to fit it. Okay, yeah, and I see another question in comparison to the Bayesian methods. How do you set the alpha and the prior? So in those examples that I showed for our results and applications, we used a uniform Dirichlet prior where we set all of the alphas equal to 1. As I mentioned, though, we could also do an asymmetric prior where not all the parameters are the same. And we did do some experiments with that. I didn't include it in the presentation, but for that we had a holdout data set from the entire population, and we used that to get an idea of which event types are more common or more rare. And we did a similar set of experiments using that prior, and we had a couple interesting results. So incorporating how common events were actually decreased the false positive rate, slightly increased the AUC metrics. So that could be like a promising area to look at, kind of more smart strategies for choosing the prior. But yeah, to begin with, and in the presentation, we just used alpha equals 1 for all of the values. So just the uniform prior distribution.
Behavior is identical for one user. And can you elaborate on the risks of change behavior due to change conditions? This is a very good question. I would say that we're not assuming the behavior is identical in the sense that we have a distribution over, a probabilistic model for behavior, which allows for some variability. But it is true that if an individual changes behavior, like we saw with the geolocation data, potentially, there's very little one can do about that. The evidence suggests it now looks like a different person. So it's a good point. I think in using these methods, I think that's the point Rachel made at the end. They're certainly useful, I think, in the investigative discovery side, but behavioral data is tricky to use, and using it in in court, I think we're definitely not there yet. So that's probably not directly answering the question, but just a comment on the question. Yeah.
Thank you, Rachel and Dr. Smith, for sharing your work here with us and providing this tutorial demonstration. Thank you for joining us. We hope you have a great day.